looks like we have almost a quorum. It's my great pleasure to welcome James Owen today. James is a reader in astrophysics at Imperial College London and a Royal Society Research Fellow. My son is also a reader, but more in books with underwear jokes and pictures, but you know, we all have our interests. And so James is really an expert in the way that stars and planets sort of evolve and shape each other together, and that those histories are intertwined. So James is here today and super busy, and tomorrow and a little bit more free, and so there's a schedule if you're hoping to sign up. But James, take it away.
Thank you, Morgan. So it's an absolute great pleasure to be here, and what I'm going to talk about is mainly some work that young people at Imperial have been doing over the last few years, trying to really get a handle on understanding planet formation. So one of the things that's changed in the last few years, thanks mainly to James Webb, is that we've been able to observe the atmospheres of exoplanets at exquisite precision. And one of the hopes, as I'll talk about, for doing that was it would teach us something about planet formation. The idea being that the composition of a planet's atmosphere traces its imprint of formation. But as I'll talk about, the theory is really letting the side down on this topic. And it's not actually a priori clear that you could do this. So what I'm going to talk about is a combination of theory and new observations to actually try and answer this question. Does exoplanet atmospheric composition actually trace formation? If it does, then it's going to open up a whole new window for studying planet formation. So I'm going to step back and I'm going to say we live in a very nice era, right? This statement at the top was sort of mainly a theoretical statement until the last few years, was that we had very strong theoretical priors that planets form in disks around young stars. But we now live in the era where every stage of this has been confirmed observationally. Right? So we know how young stars form out of the turbulent interstellar medium, and how those collapsing stars conserve angular momentum and form accretion disks. And we know in those accretion disks, observationally, this is the fantastic PDS 70 system here, where we have a protoplanetary disk here with two forming planets that are actively accreting. So we know they're growing in mass and know they're forming in this disk. And we also can observe the final stages in our planetary systems. So this is great, right? This sort of general theoretical concept has been borne out by observation. So that's actually going to be the story of this little talk, is that the qualitative ideas we have from theory tend to agree with the observations, but actually when you dig into the nitty-gritty details, things look a lot worse. So this is where we're starting from. This is an exoplanet talk, so I have to show the exoplanet population. It's the rules now. So this is a population of planet mass versus orbital period, and planet radius versus orbital period. And we've been remarkably successful in detecting exoplanets. There are now thousands and thousands of exoplanets. So if you want to ask, can planet formation models predict this population? The answer would be you go into any planet population synthesis paper and they would tell you they can predict this exoplanet population. But you have to be realistic about that. The observations have so fast outpaced the theory over the last 10 to 15 years that I don't think you can actively do that as a realistic sample. If you give the theorists the result, they are going to tell you that they can match it. So what you have to do is you have to wind back a little bit more in time, where the observations were not quite outpacing the theory, and ask, at the last point in time where the theories could make a general prediction about what the exoplanet population should look like, how well did they do? Right, so what I'm going to do is rewind about 15 years ago. So this is pre-Kepler. And this was the sort of the state of the art in terms of our prediction for planet formation. So this is a plot of predicted planet mass versus semi-major axis here, and this is the predicted exoplanet yield, right? So this is just before the launch in Kepler. And what I'm going to do is I'm going to overlay how well they did. So this is the current exoplanet population. They did really, really badly.
Very nice.
When I give public talks on this, I tend to say, I like to say this is one of the worst predictions in physics.
Oh no, cosmological concept is worse.
So, yeah, we've done badly. You might hold out hope and say, well, this detection bias line hits this here, just sits just between where we've detected planets and where the models are predicting hundreds of planets. But actually, when you do the occurrence rate studies, you actually know that almost all stars have a planet up here. So this tells you that this white region in the predicted is, we're not just finding lots of these rare planets. I think it's unclear from an observational perspective what is going on below this detection threshold, right? So whether we have lots of essentially solar system terrestrial analogs. And perhaps this is the clue as to why these theoretical predictions didn't do so well. Right? Is that if you squint at this plot, you can actually say that this is essentially a planet formation model conditioned on explaining the solar system. Right? Because that's what we knew, and we didn't like to, as a sort of community, say, well, the solar system is special, so what we're going to do is have our planet formation models generally explain the solar system and see what it predicts in terms of planets. So you can think of these as the terrestrial solar system analogs. These are your kind of ice giant analogs out here, and then you have your giant planets that sort of sit in the right zone where they're able to creep to enough masses. And obviously in 2008 we knew about hot Jupiters, so the models could explain hot. I want to sort of flip the general discussion about exoplanet biases in a slightly different way. Right? So I'm going to come at this from trying to understand planet formation. So we all know exoplanet surveys are highly biased. But a more interesting bias is if you plot the exoplanet population in this way. So this is the age of the host star, so you can think of this as the age of the planet versus its orbital separation. And it tends to be split into these two groupings. We have old close-in planets, and we have young distant planets. And when you think about how we find these planets, this distinct grouping in space and time here is actually fairly easy to understand from how the different methods work. The other thing is we have this very poor understanding in the sort of giant planet analog region. And I'll come back to this a lot later, which is sort of understanding how typical gas giant formation happens is actually fairly poorly probed by the observation. So obviously if we're finding distant planets, what we're actually doing is we're detecting them via direct imaging. So you're seeing the direct light coming from the planet. So it is easier to detect brighter planets. Planets are not stars, so their emission comes primarily from gravitational energy left over from formation. And as they contract and contract, they get dimmer and dimmer. So obviously if we're going to look for the direct light from the planet, we're going to be biased towards young planets because they're bright. For the close-in planets, we're not actually directly imaging or detecting any light from the planets themselves. What we're actually doing is we're using indirect detection methods. By this we're meaning we're looking for the influence of the planet from the star. Young stars are very active. So if you're trying to detect the influence of a planet on a very active variable star, it's going to be very difficult to find the planet. So instead, it is easier to find planets around quieter stars, which happen to be older stars. So we come back to this where these two regions of phase space haven't quite overlapped, both in age and in terms of mass. Yeah. And this is intriguing because when you do occurrence rate calculations for the young distant giant planets, you know that they're quite rare, something like a few percent. If you follow the tracks of the giant planet occurrence rate, it's rising as you go to larger and larger separations. And there are hints of a turnover, right? But we must know there has to be a turnover somewhere. So we don't have a great understanding of giant planets. And our planet formation time is limited to just a few tens of millions of years. So it's very distinctly separated in time from the bulk of the exoplanet. So getting a handle directly from observing planets forming is pretty difficult. So the hope is perhaps not to use the exoplanet population itself, but to use something else. And the hope in the future, and I've crossed out future now because this is really the present, is to probe the atmospheres of these planets and use the atmospheric composition, which I'll talk about, as a different handle on how the planets work. So the way this is working, right, is we're waiting for our planet to transit in front of the star, and some of that light is being filtered by the planet's atmosphere. Different molecules in the atmosphere absorb at different wavelengths, which will give different transit depth, and provide a measurement of the atmospheric composition. And this is really where we are in the coming decades of exoplanet research. We have James Webb now, we're going to have Ariel at the end of this decade, and the ELTs in the next few years. So they can really probe the atmospheric composition of this planet population. So the idea is that this measurements of the transit depth as a function of wavelength that you get from this transmission spectroscopy measurement tell you about the abundances of various molecules in the atmosphere. These abundances of various molecules, through some magic, which I think is uncertain at the moment, and I'm actually going to ignore the entire idea of how you go from a spectrum to abundances, because I don't think it's a settled technical problem. But these atmospheric measurements do provide some exquisite handle on the composition. And this is not a future idea, this is reality. So these are two JWST spectrum of hot Jupiters. These are the observed JWST spectrum here, and these are just sort of simple models, and you can see that as you vary the ratio of carbon to oxygen and you vary the metallicity in this atmosphere, they give detectably different atmospheric spectra. So we now have a way to say something quantitative about the composition of exoplanets. So the basic idea, and Karen's in the audience, so she was the one who sort of set the field in motion along this, is you take some atmospheric spectra, you measure some abundances, and then you try and map that into properties of the disk environment in which the planet is formed. So what's happening in this picture here is, in a realistic protoplanetary disk, what's happening is that the further you get away from the host star, the disk gets colder and colder and colder. And some of the major volatile species are able to condense out into solids. So as you move outwards and the disk gets colder and colder, you can condense out water, then you can condense out CO2, and then you can condense out carbon monoxide. And as you condense out these various major carriers of carbon and oxygen from the gas phase into the solid phase, you change the abundance of the solids and the gas as a function of position in the protoplanetary. So this means that during your planet formation process, as you acquire different amounts of gas and different amounts of solids, there should be some imprint of how you acquired that material and where you acquired that material in the disk in the planet's composition. That's the general robust picture. That's a strong qualitative statement. The problem is how you do this in a practical sense, right? How good are the models on this side to have this arrow operate in this direction? And I'm going to argue they are not good enough at all to have the arrow operate in the other direction. What I'm going to perhaps advocate is to have the arrow operate in the opposite direction, which is to use populations of planets to learn about atmospheric and disk chemistry and then learn together about planet formation. So one of the complicating factors is that while you can condense out in the disk volatiles into solids and gas phases, once you've done that, they don't necessarily stay co-located in the disk. They can actually move through the disk and move through the disk at quite different rates. The major reason for this is the transport of solids in protoplanetary disk. So in a vanilla model of your protoplanetary disk, you have surface density declining with distance, and you have temperature declining with distance. So this means that pressure declines with distance. So what that says for the gas is the gas has a pressure gradient where you have high pressure close to the star and low pressure further away from the star. So this means that the gas, instead of, when in force balance, instead of being in perfect Keplerian orbits, actually orbits in a sub-Keplerian fashion. The dust, people like to say the dust doesn't feel the pressure gradient, that is not physically accurate. It does feel the pressure gradient, but it has a density that is sort of 15 times orders of magnitude higher than the gas. So it feels the same force, but the acceleration on the dust is 15 orders of magnitude smaller. So basically, the solids operate as if there is no gas pressure. So this is a bit like cycling your cycling into the wind. If the gas is orbiting in a sub-Keplerian fashion and your particles are wanting to orbit in a Keplerian fashion, you're going to feel a headwind. This is going to slow you down and rob you of angular momentum. And the general picture is you should move inwards. So if you run a simple simulation of this, so these are solids here and gas here, you see this process happening naturally. And what you tend to find is that the solids have drifted from the outer regions of the protoplanetary disk, where you have a lot of mass in solids, into the inner regions, enhancing the solid abundance in the inner disk and depleting it in the outer disk. So this is the general picture. And the general picture has been nicely qualitatively confirmed by the observations. So this is a nice ALMA observation of TW Hydro, one of our closest protoplanetary disks, and you can see in thermal continuum, which is probing the solid component of the disk, it is significantly smaller than what is being probed in the gases. So one obvious interpretation, this is not the only interpretation of this observation, but the obvious interpretation is that the solids have drifted in relative to the gas. Right, but that's the qualitative confirmation of the idea. How well does it work practically? So if you take those simulations I said and do a more quantitative analysis, it actually fails. And we've been known about this for quite a long time. So this is a plot of the millimeter spectral index. So this is telling you something about the distribution of solids and their size distribution as a function of disk flux here. So you can think of this as a proxy of disk mass. This is where those types of simulations I showed you predict you should lie. This is where the observations are. So while we have qualitative understanding that drift happens in protoplanetary disks and redistributes gas and solids, the question of how practically that operates exactly is still an open question. One suggested scenario to explain this is those gaps and rings in the continuum are periodically slowing down and changing this observation. It's still open. And once you throw in composition of the solids, it's an even more complicated picture. Right. So instead of just having solids drifting through the disk, in the outer regions you have solids that are ice-rich drifting through the disk, and when they cross these various snow lines where the vapor wants to transition from gas phase to solid phase, then you change the size and composition of your solids, and you can change their drift rate. And if your disk has any turbulence in it, it's going to mix that gas phase turbulence up. So if we go back to our simple picture of how the composition should vary, and ask how does transport vary this? Well, if we just let the gas transport volatiles, we get different answers. So this is with no transport. You see it evolves in time as well. This is as the temperature of the disk is evolving. And then this is purely due to gas transport. And this is where this viscous alpha parameter comes in. It shouldn't surprise you to know, anyone who knows anything about accretion disk knows that the value of alpha is very poorly constrained. So having our compositional results depend on the strength of alpha is not good for a predictive model. So this is just gas transport, and if I add solid transport on top of the gas, things become much messier. So what's happening here, what's creating these giant spikes, and now my y-axis has shot up enormously, is that the solids are drifting through the disk. If they cross one of these condensation lines, the volatiles are turned into vapor phase, and they basically stop. Right? They're no longer drifting through the disk rapidly. If they stop, the fusion can send them back over the condensation line where they condense back onto the solids, and you can get large spiky enhancements of the C/O ratio and other abundance ratios at these snow lines, which you can wipe out if you make your viscous strength strong enough. It's even worse than that, right? Because all these models just laid down a temperature structure of the disk. It either evolved very simply in time or was fixed for all time. But this is problematic when you think about it. In protoplanetary disks, the dominant opacity source is the solids themselves. Right? So the solids in the disk themselves are the ones absorbing the young star's light, which is setting the disk's temperature. So if you move the solids about, then you move, or you change the temperature structure. You change the temperature structure, right? The solid drift through the disk is sensitive to the pressure gradient, so it's sensitive to the thermostat. So it's intensely cold, right? So it's actually not a priori obvious that in this coupled sense, these snow lines, or these vapor condensation lines, should actually be unique positions, right? And actually, they're not. So if you take two scenarios where you start off with a disk where basically everything is a condensed state, and you start off with everything in the vapor state, and you let these two disks evolve to what they want to be in equilibrium. So this is work by my PhD student Alpha Robinson. You actually find they evolve to two distinct differences. So there is not unique snowline positions in protoplanetary disks because of the thermal coupling between the solids and the composition. Anytime you see anything like this in accretion disks, two temperature solutions, alarm bells should go off in your head and say thermal instability. So rather than there being two stable temperature solutions, these two stable temperature solutions are actually thermally unstable, and you oscillate between one and the other. And this is exactly like the physics is identical to the hydrogen thermal ionization institute we've known in accretion disks for almost 50 years now. And this is happening on extremely short timescales, thousands of years, that the condensation lines could be moving around in these disks. So the summary should really be disk and planet formations are complicated. So the basics, so let's think about what basic predictions we might be able to make. Is there anything we can test? So I'm going to talk about some work of my postdoc here. And what she's been doing is running these kind of planet formation and disk chemistry models, but parameterizing our ignorance of all these uncertainties in the models to see if we can actually say anything. Turns out we can say something, it's just not quite what you would like it to be. So these are planet formation tracks. So what you're seeing here is the growth rate as a growth rate and position of the planet as a function of time. So you see these characteristic tracks. You tend to want to form your planets at several AU separations. Remember, this is where our observations are worst constrained in terms of the planet population. And as they get more massive, they tend to interact gravitationally with the disk, and the general picture is that they migrate towards the star while acquiring different amounts of gas and solids. And as they're doing that, they're moving through a disk whose composition in both solids and gas is evolving in space and time. So you can say general things, right? So at large separations, the volatiles that tend to condense quickest at lowest temperatures are ones that are rich in gas. So CO and CO2, methane tend to condense further out in the disk, and the solids that are more prevalent in the inner disk tend to be oxygen rich. So this is water and magnesium silicates. There are some carbon grains, and we'll come to the carbon grain or carbon solid abundance. So what happens in the outer disk is that you start off and you tend to, if you accrete a lot of gas in the outer disk, you're tending to, in a relative sense, accreting solids, that has a higher carbon to oxygen abundance than the disk on average. And because you have more oxygen-rich solids in the inner disk, as you migrate towards the host star, you tend to be polluted more and more with oxygen-rich solids. So you start off in the outer regions with a higher C/O ratio, and as you evolve towards the inner disk, this tends to lower your C/O ratio as you accrete and being polluted by more and more oxygen-rich solids. So, I think the thing to have in mind is that you want to step back from the quantitative predictions, right, which I showed you are essentially useless. Right? They are not working. But qualitative predictions, based on robust physical principles, tend to be pretty good. Right? We know about drift, and there is strong evidence drift happens if we don't know exactly how it happens. Right? We have strong evidence for, and we've seen condensation lines in real protoplanetary disks, but perhaps we don't know all the physical processes that explain them in a quantitative sense. So if we can make any qualitative statements, that would be really excellent. So one way to perhaps get at this is to think about our two standard hot Jupiter formation scenarios, right? And what the consequences of atmospheric composition in a general sense would be on this, right? So these are our two I'm not going to say preferred, let's say vanilla planet formations for hot Jupiters. There are more exotic ones, but our two vanilla ideas are that the planets, the hot Jupiters, start forming at large separations in the protoplanetary disk. The reason for this is where most of the mass in a protoplanetary disk is. But if you go too far out in the disk, you might have a lot of mass, but you just don't have enough time to form planets. So it tends to be a preferred location to form planets of a few to 10 years. So we start forming our giant planets in the outer disk, and they start migrating through the disk, and they can either migrate all the way towards the host star, become a hot Jupiter, or they can finish their migration at a few astronomical units, and then there is some dynamical mechanism, say planet-planet scattering, Kozoid-Adolph oscillations, secular perturbations, that puts that planet onto a high eccentric orbit with a pericenter that comes very close to the star, get a lot of tidal damping, and you circulate your hot Jupiter. So, again, this is a very qualitative statement. So if we go back to those planet formation models, and we separate out a hot Jupiter population that's formed by a disk migration, so these are planets that ended their migration very close to the star, from a planet population that you would say is the progenitors, the hot Jupiters that formed through high eccentric migration, so they finish their formation at a few tens of AU, then we can look at how they sit in compositional space. Right, so if you take a wide range of uncertain parameters, not a completely wide range, but a wide range, and you parameterize over our ignorance, you end up with some horrific plots. So this is the predicted C2O abundance of the planet's atmosphere versus its methods measured in O2. And you can see that you've sort of largely filled different regions of this space. But you can separate them out into different distinct regions. And then if you look in those distinct different regions and you try and separate out the blue dots, which are the progenitors to the high E hot Jupiters from the disk migrated hot Jupiters, in different regions of these parameter spaces, different relative trends emerge. So in a case down here, this is really sort of gas-dominated accretion, so you don't get many solids, and you don't have very many planetesimals polluting your atmosphere. So in this case, you tend to see sort of the orange points sit to higher metallicity and slightly different C2O than the blue points. If I go up here, which is even more gas-dominated accretion, then because the disk-migrated planets, as they sweep through the inner disk, instead of accreting solids, they're accreting gas. If I said, well, the solids are oxygen-rich, that means that the gas must be carbon-rich. So in this region, you end up with a relative trend that the blue points, the high E progenitors, sit below the disk-migrated progenitors. As you keep adding solid abundances, you tend to push this to the right, preserving this trend. And if you go into the region where you are dominated by solid accretion, then you tend to have a relative statement where the carbon to oxygen ratio is lower for the disk migrated planets, because if you're solid dominated as you move through the inner disk, then you're accreting a lot of oxygen rich solids right in the inner disk, which lowers your C2O. So the important thing to take away from this plot is that you cannot make a quantitative prediction about what the C2O or metallicity of a planet should be from a planet formation model. Right. But you can, in different regions of phase space, separate out relative trends. It does get even worse, which is the previous plot assumed that everything that I accreted is fully mixed in the planets, and therefore what I see in the atmosphere is perfectly representative of the bulk. That is not true, or not necessarily true. So you can vary the abundances between how much of the atmosphere represents the bulk. And what that does is, while it shifts everything around in this phase space, because you're not fundamentally changing the general qualitative picture of where you accrete solids and where you accrete gas, these relative trends are still preserved. There's one complication, which is where you can make this idea that when you accrete lots of solids, they tend to be oxygen rich, so you should end up with a low atmospheric C2O ratio. Because in the inner disk, many of those solids are actually silicates, which have a very high melting temperature. If those silicates, when you accrete them, go to the center of the planet and are not representative of the bulk of the planet, you actually flip this trend. So because your solids are now, your oxygen-rich solids are now silicates, which are no longer present in your atmosphere. You actually make your atmosphere more carbon. ALMA's helping-ish. Actually, no, it's making things worse. While it's providing exquisite data, that exquisite data is also telling us we have lots of problems with our triparametry disk model. One of those is that CO in the disks appears to be underabundant from our naive expectations. These are some nice results from Kizan from the MAP survey showing that this is the CO depletion factor from the ISM value in these various disks, and you can see these depletion values are significant, tens to hundreds. So this is, and our theories for why this is happening are not settled. Right? So this is problematic if we're trying to think about our planet formation models, where CO is a major volatile carrier and predicting the CO abundance, but we don't know where it is in the disk. Fortunately, playing with various scenarios to fix this problem, so taking the various solutions to deplete CO, so either you freeze them out into large solids in the outer disk where you have lots of carbon trapped at large radius, or you have some chemical pathways that convert the CO into different things. Again, what it does is it moves everything around in this space of C2O and metallicity, but all the trends still are preserved because the basic qualitative physics is still the same. And finally, disks are not 1D, shocking. So we should also bear this in mind, especially when planet formation simulations seems to suggest that planets don't accrete primarily through the midplane, they might accrete through surface layers in the disks. So I think the way to end this theory part of the talk is to say that the planet formation and disk chemistry models are great at making qualitatively robust statements. But when you ask, can they make a qualitative prediction about what planet, what specific, if you measure a specific metallicity or measure a specific C2O ratio of a planet, can you say anything about that in a formation perspective? That is an incredibly model-dependent statement. And my personal opinion is the model's not accurate enough that you can do it. So you should think of it more like this kind of plot where you have C2O here, metallicity here, but they have no numbers on the x-axis. Right. So you, in various different scenarios, you can make qualitative predictions, but you can't make quantitative. So you can't, my personal opinion is you can't use a measured atmospheric composition to say how a planet forms yet. But we can test whether planets you know form through different formation pathways have different compositions. This would be a good way to validate the picture that you can use atmospheric composition to see something about formation. So this is where the more observational side of my talk comes in, and it's mainly being led by an independent postdoctoral fellow at Imperial, James Kirk, who was actually a postdoc here at the CFA a few years ago, the Align Data University. So the idea is to try and separate out planet populations you think have an idea formed differently, and then go look at their atmospheric compositions and say, are they different? So does atmospheric composition actually create? So an idea to do this is this very nice plot here of projected obliquity. So this is the angle or projected angle between the star's spin axis and the orbital angular momentum of both planets. So this is an empirical result that hot Jupiters appear to have basically zero obliquity at around cool stars, but a range of obliquities around hot stars. So you can either say you only form disk-migrated planets around cool stars and you formed a planet through a wide variety of mechanisms around hot stars. That seems a little unrealistic, that a forming planet knows something exactly about the temperature of the star. But this temperature of the star here is actually associated between when you switch from a convective envelope from the star to a radiative envelope. Convection is much better at dissipating tides. So the idea is that obliquities, while they might have a wide range to start, can be tidally impacted around cool stars, but they cannot be around hot stars. So perhaps you could say that these, with low obliquities here, these could be our disk-migrated planets. I'm not doing very well with this slide. But with the higher obliquities, these are our high eccentric planets. Right? If you have some scattering event, that's not going to necessarily put you in the same orbital plane as the disk-imaged planets. So the idea is that aligned planets might point to a disk migration channel, and misaligned planets relative to the stellar spin axis might point to a high eccentricity formation path. So now we have a way to dynamically separate, independent of their actual formation, of saying how we think planets might appear. So we have a sample here of 8 planets, 4 of which are aligned, 4 of which are misaligned, and they're all above this transition from convective to radiative envelopes. So you might think there are obliquities persist. So let's be more optimistic and say, basically, all possible parameters in my planet formation model, even though I don't know what they are, reality is not just going to be a Monte Carlo simulation of all possibilities. It seems unlikely. There's probably a more favored value of alpha, a more favored value of the Wilson observation. So if you pick an individual model, formation model, you actually see at high metallicity, you get a distinct separation in C2O and metallicity to these 2 different formation channels. And these error bars are realistic JWST error bars. So you should be able to test whether atmospheric composition is different in these 2. So we have all our spectra now. Well, we have 6 planet spectra, sorry. There's 8 in the sample. We have 6 planet spectra. This is the first one that's been published. You can see water, you can see CO2, you can see hints of CO. We can see SO2 as well, which is very interesting from a completely separate region. We also have a mystery absorber that we don't quite know what it is. One suggestion is OCS, but I'll leave it there. So this is the first of our published spectra. We have preliminary spectra for the other 5 planets. So we can answer this question. Does atmospheric composition actually trace formation? So what I've done is I've normalized all these spectra to the planet scale height. This is a natural scale here, and plotted all the spectra. And things pop out slightly. In this region where you have the water absorption feature, your orange points, the line spectra tend to sit above the blue in general. Same here. They've actually all been normalized to the same absorption here. So the fact that they look similar here is by design, not but if I bin up my spectrum, it becomes even more obvious. So this is the binned misaligned spectra, and this is the binned aligned spectra. So you clearly have a different water absorption in the aligned spectra here and here. So I think the answer is, does atmospheric composition actually trace formation? I think this is showing that it does. We have 2 populations of planets we thought formed through different mechanisms, through dynamical arguments. We've gone out and measured their atmospheric spectra without the expectation of what the exact composition should be, just to compare them in a relative sense. Because our qualitative predictions are more robust than our quantitative predictions. And we have a qualitative difference between these 2 spectra. So you can see that basically these are all in prep. So the actual result is very preliminary in what it means in terms of planet formation. I think the naive guess that you should say, I see more water in the aligned spectra, is not quite true. It matches with that qualitative prediction that as you go into the inner disk, you accrete more oxygen-rich solids, you should have stronger water absorption. But the relative height of the CO2 and water feature peak are actually sensitive to bulk metals. So we need to wait for the retrievals, which are less trustworthy, to pin down whether it's actually a difference in bulk metallicity or it's a difference in composition. All I can say at this stage is they're different, which is positive. So perhaps what we should be thinking about is, instead of trying to measure atmospheric spectra and then asking how does that compare to our qualitative planet formation models, and then saying, oh, this one has a C2O ratio of this value and a metallicity of this value, this model says it formed by this metallicity. What we should actually do is measure the compositions of planetary populations, see what that says in terms of our scattergun of planet formation models, say, oh, that to match those quantitative values that required our planet formation models to have these types of parameters, right? And then go, does the planet formation and disk composition models that match our observations on this side match our observations on this side? I think that's the way to make progress. So I don't think we should be thinking in this direction as a field. We should actually be thinking in this direction. But the answer is perhaps in measuring the atmospheric composition of planets, asking what does that imply about their formation, and then saying, does that, from our model predictions, agree with the observations we have in the system? In the last few minutes, I will talk about how to push this a bit further. Right, is that the easiest way to start was to separate these hot Jupiter populations from disk migrated to hot Jupiter, from disk migrated to highly E-migrated. But actually, hot Jupiters are not the most common type of giant planet. In fact, they're extremely rare. The warm Jupiters are actually much more common. This is the giant planet occurrence rate is strongly rising to larger and larger separations, and there's hints of a turnover at large separations. Now, because these hot Jupiters have this quite strong dynamical formation pathways, they're actually distinct in a dynamical sense from the warm Jupiters. One way to show this is just to look at the companion fraction of these two populations. Hot Jupiters, by and large, are basically on their own. Warm Jupiters, by and large, often have a close-in companion. Often that close-in companion is actually very small. So this has a very interesting consequence. Small planets tend to migrate through disks rapidly. Large planets tend to migrate through disks slowly. So how can you have a large planet and a small planet close together? It just doesn't make any sense. Actually, the dynamic simulations give you the answer, which is that the giant planets are so disruptive inside 1AU, they actually disrupt the disk enough to slow down the small planet's migration. So if you trace back this in time, what you actually find is that these giant planets can't have migrated very, very far. So they actually probably formed in the inner disk, not where we see them today, but close to where they see them today, and they've migrated nowhere as far as the hot Jupiter population. So hot Jupiter should experience strong migration, whereas dynamic argument says that warm Jupiters with inner companions might have experienced weak migration. So if they've only ever accreted material from the inner disk, then if they accrete gas-rich material, that tends to be very carbon-rich because all the oxygen is in the solids, but if they predominantly accrete solids, then their compositions will be very oxygen-rich. So we can actually, instead of having a two-type comparison between hot Jupiters and that might form through high excitatory migration and disk migration, can actually extend this to a triple prediction, which is much stronger. We've actually submitted a proposal to go do this same experiment now, but for a population of warm Jupiters with inner companions, and then hopefully we can confirm this idea that atmospheric composition does actually trace formation. Once we've proved that, then we can ask the question, what does that imply about planet formation? So, I'll finish there. So, planet formation has been notoriously bad at making quantitative predictions. Well, it's made lots of quantitative predictions, they've just often not been great. But it's very good at making qualitative predictions, because the basic physics is very simple. So we can robustly predict trends in atmospheric composition. This aligned program being led by James Kirk, with a lot of help from the Bowie collaboration, which is the atmospheric observational collaboration primarily centered in the UK. We have got atmospheric spectra for aligned and misaligned planets. The preliminary results show a qualitative difference in the spectra, which I will interpret as atmospheric composition really does actually trace formation. And we can extend that to different dynamical populations. But what that actually means for planet formation, I don't know. But I'll leave it there. Thank you.
Questions for James?
You discussed the planets and you discussed CO as an important tracer of the history, but there is also the metallicity of the star itself, because these solids end up in the star, even before they start making planets. So, the disk starts with a large mass, and some of it accretes. And so my question is, how does that constrain the models? And the second thing is, how much variation there is in CO for stars?
Great question. So on the first question, yes, you're right that any solids that end up in planets or in planetesimals don't end up in the star. In fact, we have the same trend for the sun. The sun is actually depleted in refractory elements by a small factor relative to other sun-like stars. The depletion is actually extremely small. It's only a few percent, which is why you can measure it accurately for the star. The reason for this is that it takes a lot of solids to pollute the young stars, especially when they're convected. The hope is that that argument for using stellar spectra to constrain formation will work better for the more massive stars with the Gaia planet population. So that is another way to get a handle on this. In terms of the C/O ratio abundance for the stars, there is a large-ish amount of scatter in the star abundances, but it is way smaller than the expected scatter you get from the planet formation models. Not surprising, right? Planet formation is a very messy thing, so it can take, and chaotic, so it can take smallish differences and magnify them.
Yeah, your history of the quantitative predictions reminds me of, I was listening to a talk by Doug Lynn many years ago. It was before the first exoplanet had been detected. And he was talking about planetary systems, and he was going on and saying, well, the usual case this, the usual case that. And I said, well, Doug, what does the usual case mean? Because there's only one planetary system that we know. And he said, the solar system, that's the usual case. And then everybody laughed. But then it turns out he was serious because in some Bayesian sense, he made this prediction based on the expectation that planetary systems would all behave like the solar system.
Yeah, and it's, well, Doug's not here to wind up. I mean, the next talk, at lunch, I will talk with stuff I've done with Doug, so Doug's great. But yes, he is one of the originators of this extremely bad prediction, which is fun to remind Doug about. So there was a series of papers in the early and late 2000s making a series of predictions along with this conditions on the solar system. It's actually an irony, which is Kepler was such a magnificent success because they massively over-engineered the telescope to find these planets. So if the predictions had been right, Kepler would have been a very different mission. Right? Oh, we'll only find a few hundred planets. So we can thank these predictions for making Kepler so strong. So yeah, we have to be careful. Right? It's the standard astronomers worry, right? Is the one object I'm conditioning all my theory on a representative object, and it turns out for the solar system and planetary systems, no. Which is again a very interesting question. Why is the solar system so different? And it actually comes back to the stellar atmospheric composition being depleted in refractance. This is a very interesting clue as to what is going on, as to why the solar system might be so different to typical exoplanetary systems. So, you can ask me about that later.
Thanks for the talk, James. So the systems you're typically looking at are hundreds of millions of years old, billions of years old, right?
So,
Because you're going after the hot Jupiter population.
so the hot Jupiters are all billions of years old.
Yeah. And we know that disk dispersal is taking place on a few millions of years.
Exactly.
So there's a big gap in the
Exactly.
picture. And I wondered if you'd comment on the complication of volatile delivery to this picture that you're presenting.
Yeah, so, yeah, that's a great question, which is when does the atmospheric composition actually get frozen in? Right. If you have, so one of the things that pushes the planets to extremely high magnetism, it's going to take a while to get them, it's like those are built in, is this later time delivery of planetesimals. So here we are. The kind of thing that's pushing you out here, right? So this dividing line here, gray divided line, this is you don't accrete a lot of your solid abundance through pollution by planetesimals, and here you do find pollution by planetesimals. So I think what's going to be really interesting is once we have the actual inferred metallicities and C-to-O ratios from our different spectra, right? Where is it putting you in a general sense on this plot, right? Is it pushing you towards planetesimal accretion late, or is it pushing you towards, say, pebble accretion early? I'd say that the hints at the moment is that it is actually late time process. The third methodicity of at least we just discussed the dangers of discussing things on one result. So we have a retrieval of this planet, and it is pushing it to high methodicity, which is suggestive of late time processing. So if this one planet is representative of all planets, then I think late time delivery by accretion of planetesimals as you sweep through the
Awesome talk. What was the distribution of aligned and non-aligned planets in the JWST survey that you showed?
So we have 4 in the survey. So it's one of these things, right, that it's great to do with JWST is you come up with an idea, then you select some planets and you realize, other people have gone after some planets for different reasons, but they happen to satisfy my criteria. So our specific survey, which is being led by James Kirk and Eva Maria, we have 6 planets, but there are 2 that have also been observed by JWST that satisfy their criteria, and one is a misaligned and one is aligned. So when those spectra become public, then we'll grow to 8. At the moment we have 6, and we will be 8. We're not actually, the people involved in these other surveys know about this and are quite happy to attach their results to this. So I don't think we have access to the 2 other spectra. In terms of how many there are available to do this, there is about 18 planets in total. But as with everything, right, you select the best to do your observations, and then the more you add, the signal to noise adds. What James Kirk did in developing this survey, and one of the things you always have to satisfy when you write your telescope proposal is, how do I justify my sample size? And you can show that as you progressively add more and more of those planets to the sample, they don't add a lot in signal to noise, assuming everything is the same. Right. If there's testing the bulk thing, and then what does the distribution look like? And I think that latter point is where we should go after the other 10 planets. Is everything peaky, right, or is there a smooth distribution?
So I feel like sample size is one issue, and another issue that you kind of mentioned, but like sort of swept under the rug, was uncertainties in the retrievals. So am I right in thinking that this like paradigm shift that you're suggesting with the directionality of what we can learn quantitatively and qualitatively about planet formation and atmospheric composition, you're kind of implying that like the quantitative uncertainties in retrievals are better than the quantitative uncertainties in like planet formation models and disk.
For it to work like that, yes, that would have to be true. I don't think that's been proved yet. In fact, probably what people have proved is exactly the opposite, which is when they take the same data, run retrievals, they get different answers. I think retrievals, the concept of a retrieval and how it will work is correct. Right? I think it's a technical challenge that needs to be satisfied over the next few years as to how to deal with that in order to allow this paradigm shift in directionality that we're thinking about as well. That's why I find this plot so compelling. Right? If I came here and told you, oh, here are our 4 planets, and here are our 2 posterior plots for our retrievals, look, they're different, you wouldn't believe me. Right? I wouldn't believe me. I think seeing it with your eye like this is a much more compelling way to say they're different. What this means might take a long time.
Can I ask a question?
Not sure it won't. And only because it's you and you asked so nice.
Actually, you don't have to answer. It's a question you don't have to answer, but I think it's an interesting exercise. If one had only measurements of the emergent spectra of the 4 outer planets of the solar system, what constraints would one really place on their formation history? It seems to me in the solar system, most of the constraints on the very interesting formation history come from the architectures, the resonances, the orbital periods, the inclinations, the obliquities, the small bodies where they exist and where they don't exist. And so I wonder whether this entire endeavor might be informed by the lessons of our own solar system.
I think that's an exactly fair point, right? And I have taken the solar system's picture in order to set up this whole paradigm, that is using dynamics to say something about formation. Exoplanets does have this one unique thing over the solar system planets, is that because they're so hot, all the water is in the atmosphere. So we have, it's one of the strange things, right, is we actually have constraints on what the major oxygen carrier is for exoplanets, whereas we don't for the solar system planets, which I think is strongly hindering them. I think actually in the solar system, in terms of composition, a lot of the interesting compositional constraints are coming from the Nobel gases, because they're the simplest that don't participate in the
Very interesting.
Okay, let's thank James again.